Hello everyone, I'm Norman Wahlberger. This is our second video on Euler product and zeta functions. We are looking at this from a box arithmetic point of view. So we've identified something that we might call the fundamental identity of arithmetic, which is largely equivalent to the more usual fundamental theorem of arithmetic. And we express it here in terms of this series of boxes which are being careted together to form this beautiful M set or box with just the natural number starting from 1 in it. So here we have powers of the prime 2, here we have powers of the prime 3, powers of the prime 5, of the prime 7, and so on. So we form the caret over all primes in this fashion. And I remind you that to form the caret of two boxes, we take the box consisting of all possible products of elements, one from here and one from here. Now, because these are unbounded objects, we require a different kind of theory. So we need to go beyond what we've already set up. And I'm not going to do that today. So we are just going to think about this sort of informally. But generally our orientation is that we're going to try ultimately to assign meaning to something like this in a finite way. We want to always avoid the assumption that we can do an infinite number of things, because we can't. So we have to try to state what we're talking about here. We have to bring out the meaning of such an equation in a purely finite way. Okay, so today what we're going to do is we're going to take this fundamental identity and we're going to augment it in certain ways, moving towards the Euler product for the zeta function. But the zeta function is, from my point of view, not really a proper mathematical object, and neither is the Euler product. Nevertheless, we're going to be moving in that direction, and we'll see that we are touching base with a wide variety of interesting things. And in fact, we'll be able to, even from just this elementary point of view, without any prior understanding of the zeta function or any of the associated number theory, we're going to be able to see how the zeta function story somehow has an intimate connection with prime numbers and the general growth of prime numbers. So we'll be able to access some of that in a very elementary way here. Okay, so just make sure that we understand how to form the caret of two boxes. Here's a box with elements A, B, another one with elements C, D. The caret of these two boxes is the box consisting of the elements A times C, A times D, A times E, B times C, B times D, and B times E. So now in the world of boxes, you can always square any box, and just by multiplying a box by itself. And this property pleasantly has this property, just follows from the associative law, that the square of A times B is equal to the square of A times the square of B. So when we're talking about squares of elements, there's in the box world, there's various levels at which we can kind of apply an operation like that. So instead of just squaring a box, we could also do something sort of one level down, by which I mean square the elements of a box. All right, so given the box A, we could look at the box consisting of the squares A squared as little a runs through the box capital A. So for example, here's a box with two elements, number 3 and alpha. If we apply this f to it, we square 3 to get 9, we square alpha to get alpha squared. So that's what f does to this box. It's not really squaring the box itself, it's squaring the elements in the box. And then we get an interesting connection with the caret operation, because f of A caret B is f of A caret f of B. So, for example, here, if we take this identity here and we consider forming this f to all the ingredients. So f of this thing would just be the box A squared B squared. F of this is the box C squared D squared E squared. So if we caret those, we have to form all possible products. A squared times C squared, A squared times D squared, etc. But A squared times C squared, by this rule here, is the same as A times C squared. So what we see is that as we run through all 6 possible combinations, what we're getting are just the squares of all the elements over here in the caret of these 2 original boxes. Okay, so if this is box A and this is box B, this is box A caret B, then f of A caret B is this, and f of A is here, and f of B is here, and we see the identity is valid. So now let's take the fundamental identity of arithmetic, and let's apply this f operation to both sides. So with this m set consisting of the powers of 2, we're going to square all of those elements. So there's 1 squared, 2 squared, 2 squared, squared, 2 cubed, squared, etc. Similarly, we're going to square all the elements in the m set consisting of powers of 3, and of powers of 5, and of powers of 7, etc. And according to the identity that we've just established, on the right-hand side, what we should be getting is the m set consisting of the squares of the natural numbers. And I hope you see this is not surprising at all. I mean, if you take some element here, for example, 4 squared, and ask, well, how can you get 4 squared by taking products of things like this? Well, you could do it here. You could take 2 squared squared times 1 squared. And that's the only way you can get 4 squared. Just in the same way that the only way of getting 4 is to take 2 squared times 1. Okay, so now let's just rewrite this a little bit. So instead of having the squares of all of these things, let's put the squares right above the 2. So, for example, this next one over here would be 2 cubed all squared. Let's rewrite that as 2 squared all cubed. Right? Then what we have here is an m set consisting of powers of 2 squared. And over here we'll have an m set consisting of powers of 3 squared, and so on. On the right-hand side, we still have the same thing over here. And now we can try to sort of connect with the sums that are appearing in the zeta function and in the Euler product formula by applying what we call the summation, or the sum operator, capital S. I remind you what that does is it takes an m set and just takes the sum of all the elements of that m set. And we saw that S of A caret B equals S of A times S of B. So this summation operation works well on carets of things. So let's apply S to both sides of this thing that we've just obtained, this thing here. So S of this one here is just the sum of all the elements. That's the series, in quotes, 1 plus 2 squared plus 2 squared squared plus 2 squared cubed, etc. And S of this thing is the sum of all the powers of 3 squared, so it's 1 plus 3 squared plus 3 squared squared, etc. And then similar one for 5 and 7, etc. And we're going to multiply all of these sums. That's what's being described here. Now, this sum here is like a geometric series, okay? It starts with 1, and then there's the common ratio is just 2 squared. At each stage, we're just multiplying by 2 squared. So if we liberally apply the standard formula for the sum of an unbounded geometric series, it's 1 over 1 minus this common ratio, 2 squared. Okay, so this is all informal. We're just trying to get an idea, get our heads around this, and see if anything comes up that might be interesting and worthwhile. So at least formally, this geometric series is represented in some fashion or other by this term here. Similarly, there's another geometric series with first term 1 and constant ratio 3 squared. So its sum, in some sense, is 1 over 1 minus 3 squared. The next one will be 1 over 1 minus 5 squared, etc. And on the right-hand side is this the sum of these guys, just the sum of the squares, 1 plus 2 squared plus 3 squared plus 4 squared, etc. So a literal application of this rule in this context seems to give us something which doesn't have any, say, immediate sense, okay? Although it's possible that perhaps, there's some interpretation of these unbounded objects for which some kind of equality like this has some kind of meaning. But certainly currently, this doesn't look like it's very promising. I mean, these things here are, these are negative numbers, and they're getting bigger in the denominator. So this whole thing is getting smaller, and and this one is obviously getting bigger. At least if we sort of proceed in terms of partial sums. So the validity and the meaning, in fact, of something like this is very much in question. But nevertheless, this is in the spirit, in the direction of the Euler product for the zeta function. So let's keep going a little bit further with it. What made that work is that the squaring operation has the property that mn squared equals m squared times n squared. But that property, that sort of multiplicative property, is shared by lots of other things. For example, cubing. It's also true that if you cube m times n, you get m cubed times n cubed. So in fact, the same reasoning allows us to replace all the numbers in the fundamental identity with their cubes. So here are the powers of 2, and we're cubing all of them. Here are powers of 3, we're cubing all of them, etc. And we're always going over all primes. So the first one is 2s, then 3s, then 5s, then 7s, then 11s, etc. And on the right-hand side, we just get the m set consisting of the cubes of the natural numbers. And again, the meaning is the same as before. If we take any one element in here, okay, then it's obtainable in exactly one way as a product of something in this first box times something in the next box times something in the next box, etc., where most of those product constituents are ones and only a finite number of them are not. Okay, so again, we can perform the same little twist where we interchange the powers here. So instead of having 2 squared cubed, we could write 2 cubed squared. Then we see that the entries of this thing here are just given by this geometric sequence. Each term is 2 cubed times the previous one. And similarly here, geometric sequence. Each one is 3 cubed times the previous one. And then when we apply our S operator, well, again, we have a geometric series. First term 1, constant ratio, the prime cubed. So in general, it will be 1 over 1 minus p cubed. And we're taking the product p over all primes. It's a quick way of saying what we get when we perform the sum of all of these guys and multiply them all together. And over here, well, we're just getting the sum of all the cubes of the natural numbers. And again, this is a highly questionable thing for exactly the same reason as the previous one was. This seems to us to be unbounded and not even vaguely approaching anything. And these things here are all giving us something completely different from what appears to be happening on the right-hand side. Nevertheless, it's still kind of interesting. So here's another variant now, which is not, we're sort of stepping away from box arithmetic generally and just focusing on something that we can do with these boxes of natural numbers. So in our world where we accept rational numbers also, we can take reciprocals of natural numbers, and those are fractions or rational numbers. So that's perhaps something else that we could do, is to take reciprocals of everything in the fundamental identity of arithmetic. And the reason why that works is because taking reciprocals still obeys this fundamental sort of multiplicative property, that the reciprocal of n times m is n inverse times m inverse. So here are the powers of 2, and we're taking reciprocals all of them. Here's powers of 3. We're taking reciprocals of all of them and carroting everything together. And on the right-hand side, just the reciprocals of the natural numbers. So now let's apply the S operator. Okay, maybe we could rewrite this first of all as 1. Here's 1/2. Here's 1 over 2 squared. Here's 1 over 2 cubed. It's another way of writing it. Here's, again, it's sort of a geometric series, but now the ratio is 1/3. Over the next one, the ratio will be 1/5, and so on. And on the right-hand side, well, we just get the m set of the reciprocal natural numbers. Okay, what happens when we apply S now? Well, now this is a geometric series of sort of a different kind. it's something that's more familiar to us. We're more comfortable with assigning a meaning to this unbounded, ongoing sum. Now, this is the kind of sort of infinite sum where there actually is a way of assigning a meaning to it. Okay? And the reason is because the end result is a number that we already have obtained. It's already a known rational number. So if you add up this thing here, 1 plus a half plus a quarter plus an eighth, etc., the total is 2, which according to the formula is 1 over 1 minus a half, so that's a half. In the bottom there we get 2. Okay, now that's different from the usual thing that I complain about, because now we have an infinite series which is summing up to a rational number. And the point is that we can make sense of that statement without requiring us to do an infinite amount of work. We don't have to do an infinite amount of work to get the thing on the right-hand side because it's already a known rational number. Okay? And then we can state the meaning of such a statement in terms of approximations. We can say, well, if we take the first k terms, of the left-hand side, then we're within such and such of the end result 2. So that's in dire contrast with the usual story where we have some sequence of rational numbers or some series which supposedly converges to an irrational number. The problem there is that the irrational number has not been brought into being except by the actual process of creating this infinite series. You have to run the infinite series to the end before the irrational number, which is the limit, is even obtained, before it comes into existence. Right? There's a huge difference between these two scenarios. One of the reasons why we really want to stick to rational number arithmetic if we want to do mathematics properly. This is such a profound understanding, okay? And I know it's going to be hard for many of you to accept because you've been taught from an early age something different, but this is the way the world really is. Okay, so we actually can have legitimate meanings to these various sums in each one of these things. So here we're going to get 1 over 1 minus a half, 1 over 1 minus a third, then 1 over 1 minus 1/5, etc. on the left-hand side. And on the right-hand side, well, we get this series. Okay, which is more problematic because here there's not an object that's known to us, which is at the end of the rainbow. And of course, all students of mathematics will know that this is a series which diverges in the usual sense. So let's have another look at this sort of strange identity that seems to be appearing here. So we have 1 over 1 minus a half times 1 over 1 minus a third times 1 over 1 minus 1/5, etc. And over here, the harmonic series. Well, this is 2, and this is 1 over 2/3, that's 3/2, and this is 1 over 4/5, which is the same as 5/4, and then the next one will be 7/6, and the next prime is 11, so it'll be 11 over 10, and the next one is 13, so it'll be 13 over 12. Now, all of these quotients that we're getting are pretty close to 1, because they're a prime divided by 1 less than the prime. And as the prime gets big, that quotient will start to approach 1 from on top. So what we're doing is we're multiplying a series of things here together, and we're always multiplying by something that's a little bit bigger than 1, okay? But as we proceed, the separation from 1 is decreasing. So we're getting closer and closer to multiplying by 1, although we never do. So it's a natural question maybe to ask, well, if you just started computing these partial things and just recorded it and looked at the totals, what's happening to those totals? And at this stage here, we see that this is probably telling us something. This is suggesting to us, because let's say we know that this diverges, it's suggesting to us that this is going to diverge as well. Right? It would be rather strange if this thing here converged to something like 13.5 and this diverged. So that's telling us something about the prime numbers already, actually. It's telling us something about how sparse they are, or how not sparse they are. The fact that this product presumably diverges. It's giving us some kind of information about the large-scale growth of prime numbers, sort of in a large-scale kind of way. So let's do one more variant, which moves us quite close to the Euler product story. But also brings suddenly into being this idea that actually we're doing something non-trivial here, that we're actually touching base with some subtle and actually rather delicate mathematics, just from this sort of elementary arithmetic with these boxes and carets and forming sums. So the variant is that we're going to replace all numbers in the fundamental identity with their squared reciprocals. Not their squares, not their reciprocals, but the square of their reciprocals, or the reciprocals of their squares, same thing. So, looking at the first box with powers of 2, we're taking all those powers of 2 and raising them to the -2 power. And same thing with the box of powers of 3, etc. And on the right-hand side, well, we're getting the box consisting of all the squared reciprocals of the natural numbers. Now this first box here, we can write it as 1. This one here is 1 over 2 squared. This one is 1 over 2 squared squared. This one is 1 over 2 squared cubed. We do the same thing as before, always interchange the order of the powers, okay? That makes this also into a geometric series. Same thing with this one and also with the next one, etc. Here the ratio is 1 over 2 squared. Here the ratio is 1 over 3 squared. The next one, ratio 1 over 5 squared, etc. And on the right-hand side, the m set of reciprocals of squares of natural numbers. Now let's see what happens when we apply S. And suddenly something really interesting comes into focus. So here I've copied what we've just obtained. Powers of 2, reciprocal squares, powers of 3, reciprocal squares, powers of 5, reciprocal squares, etc., careting them all together, and here is the m set of the reciprocal squares of the natural numbers. Okay, each of these inside is a geometric series when we apply our S summation operator. So we take the sum of all these guys, first term 1, ratio 1 over 2 squared, so we get 1 over 1 minus 1 over 2 squared. Next one, first term 1, ratio 1 over 3 squared, so we get 1 over 1 minus 1 over 3 squared, times 1 over 1 minus 1 over 5 squared, etc. And on the right-hand side, the sum of the reciprocals of the squares of the natural numbers. So what does this look like in practice? Well, this is 3/4 over here. When we take the reciprocal, we get 4/3. Here we have 1 minus 1/9, so it's 8/9, reciprocal 9 over 8. Over here, 5 squared is 25, minus 1 is 24, so we get 25 over 24. The next one is 7, we get 49 over 48, and so on. So now we have the squares of the primes in the numerators and 1 less than each of those in the denominator. Now, the right-hand side, however, is very different from the previous one because there's a square there. And Euler famously realized that this thing sums not to infinity, it doesn't go on and on. It actually sums to something that he was able to identify in terms of pi, famously pi squared over 6. So that's certainly one of Euler's great, remarkable formulas, which made a big impression on everyone. It's still a remarkable kind of thing. Even though, strictly speaking, you know, what is pi? Well, we don't really know. And actually this sum, strictly speaking, also, it doesn't really work. But there's something going on here. Okay, definitely there's something going on here, something like magic. So, but now what we have is, from this box arithmetic point of view, is some kind of identity like this, that if we're assuming Euler's result, and we suppose we have some approximate meaning to this, it means that the product of these squared primes divided by the one less than them, that is very likely heading towards something actually reasonably concrete. It's like a region on the number line, maybe not exactly a point, but some kind of object on the number line. So this is now interesting, and it's decidedly different from the previous one that we had, where we were just looking at products of primes over primes minus 1. Great. So now we actually can make a calculation. Okay? Let's choose the first primes up to 100. So 2 squared, 3 squared, 5 squared, 7 squared, and all the numbers less than those. 11 squared, 13 squared, 17 squared, all the way up to 79 squared, 83 squared, 89 squared, 97 squared, the last prime before 100. Okay, so that's sort of an initial sequence of the left-hand side of what we were obtaining. And this thing here, okay, it's a rational number, and we can approximate what it is numerically. My computer tells me it's approximately 1.641945. And what is pi squared over 6? Approximately, okay, in quotes, because pi really is not a proper defined number, but approximately, it's 1.644934. So the claim of that formula that we had is that if we keep on doing this by multiplying by further and further problems, we should be heading towards this number. So this number here is getting bigger a little bit at a time. And I want you to think about this in terms of like perhaps interest payment, okay? Let's say we're at this stage here. We've computed this thing here. What does it mean to multiply by 121 over 120? Well, this is a little bit more than 1% more than 1. So it's something like 1.01. So this is like how much you owe if you borrowed this amount of money for 1 year at a roughly 1% interest rate. Okay? This little ratio here is giving us 1% interest. So the amount that you owe after a year is a little bit more, roughly about 1% more, a little bit more. Okay? Now, the next year, well, we're talking about 13 squared over 13 squared minus 1. That's a little bit closer to 1. So the interest rate has gone down a little bit. Maybe it's 0.8 or something like that, or 0.9. Okay? So your principal that you're going to owe after that year is still going to be bigger, but it's going to be bigger by geometrically less than it was the previous year. And that's carrying on. So the interest rate every year is decreasing. It'd be nice if banks did this, but anyway, the interest rates are decreasing and heading towards zero. But what we're saying is that the total amount that you're going to owe as you keep on going is going to head towards this thing here. Now, on the other hand, on the right-hand side of the equation, we had this sum of the reciprocal squares. And we can calculate those as well. That's just a very explicit calculation. So I summed k equals 1 to 300. My computer told me that's about 1.641606, which is pretty close to this thing here, right? So you see, there's two different ways of calculating something, right? This calculation here is, in some sense, calculating the sum of the squared reciprocals of the natural numbers from k equals 1 to 300. Or reciprocally, this thing here is calculating this product over primes of these things here. Now, which of those is more work? I don't know. But you see that there are two quite different things here that are being compared, and we're actually touching base with some real mathematics here. Having to do with partial sums of this thing, and having to do with partial products of this thing, and some kind of closeness between these two things. Now, at this stage here, we can also perhaps appreciate that this kind of information is telling us something about the growth of primes. So just let's suppose that we sort of stop at this level here and pause for a second and ask, okay, what's going to happen from here on? Okay, so if the primes from here on get really far apart and they get big fast, okay? If the primes are big, then we're going to be multiplying by numbers which are really close to 1. The interest rate will be very close to 0. Then it's possible perhaps for us to make a computation that shows that we're not going to be able to get from here to here by continued multiplications by these further ratios if the primes are going too fast. Okay? So the fact that as we keep on going, we're going from here to here is telling us something about the growth rate of primes. If the primes are growing too fast, we're not going to be able to get to here. On the other hand, if the primes are not growing fast enough, if there's a lot of primes, say between 100 and 200, then we'll be multiplying too often by interest rates which are still reasonably big, and that's going to bump us over going from here to here. For example, if you have an interest rate of 1% and you have that for 20 years and compound interest, you're going to probably pay something like 22 or 23 cents, on your original. So multiplying 1 by 1.23 will definitely bump this over that, right? So that's the kind of reasoning that allows you to see that this scenario is going to allow you to extract some information about prime numbers. Now this is all very primitive, of course, but you think about the Riemann zeta function and the associated number theory as encoded by the Riemann hypothesis as being some much more sophisticated analysis, somehow in the same direction. Okay, that the form of the zeta function and these sums tell you something about primes. And what I'm trying to convince you today is that you can see some of this, at least in an elementary fashion, without any complex numbers, without any supposition that there is such a thing as the Riemann zeta function. You can see this simply as consequences of formulas that are obtainable from the fundamental identity of arithmetic, okay, by suitably applying multiplicative functions to this identity in box arithmetic. I'm Norman Wildberger. Thanks for listening.